Can I start?
One moment, please. It's just
Sure. So some of them will not join from the Zoom, but from some other link.
yeah, YouTube.
Uh-huh.
So we are live streaming on YouTube.
How
Just
many people? How many people are there usually?
just a moment. Okay. So welcome everybody to this fixed Majorana-Raychaudhuri seminar series. It's a pleasure to have Dr. Ye-ling Zhou, and he's going to talk about testability of grand unified theories in neutrino experiments and gravitational wave experiment. When
Okay.
I can send you a reminder when 5 minutes are left.
Okay. Thank you. Thank you very much for the invitation for this seminar online. I will talk about my recent series of work in the grand unified series, for its connection with neutrino experiments and gravitational wave measurements. Yeah. Okay. Grand unified series is some kinds of, some kinds of theoretical framework, trying to unify all known fundamental particle forces, including the electromagnetic force, weak force, and a strong force. Probably some other new forces there. We don't know. It follows the history of the paradigm of the unification, like such as the unification of the electricity with magnetism, and then the partial unification of the electromagnetism with the weak interaction. So we don't know if the weak interaction and the strong interaction can be unified or not, and that this hypothesis is some kinds of unified grand unification. This is what we know about the particle physics today. Mainly the standard model. It's built in the gauge series with of three gauge series: SU3 cross SU2 cross U1, SU3 for strong force, and SU2 cross U1 for the weak and electromagnetic forces. And the particles, all matter particles, including the neutrinos, charged leptons, and the up and down type quarks, three flavors. Okay, and the mediators, this photon, gluon, and WZ boson, and one more scalar boson, that's the Higgs boson. So beyond the forces, we have the Yukawa interactions together with the Higgs mechanism. It give us the masses for fermions, and the Higgs mechanism is the mechanism to break the electroweak in the symmetry. But something that is not included is the neutrino masses. We have neutrino oscillations, which prove that neutrinos have masses and leptons can mix. Well, how to get a God? First, we should have the unification of symmetries. There should be a larger group, including the SU3 cross SU2 cross U1. If this group is a simple Lie group, and then we have the unification of couplings. That means the G3, G2, and G1, they should be unified at some scale, and that scale we call it M-God, the God scale. Finally, the unification matters. Since we have to be consistent, all the matter field should be consistent with the group at the frame in this framework. Then how the leptons and quarks should be unified in the representations of the group, it makes sense. Well, the first step to the grand unified theory is the Paddy-Standard model. It unifies the leptons with quarks by considering the leptons as the fourth corner of quarks. So the corner symmetry now is considered as SU4 instead of SU2. In the in their later paper in 1974, the electric interaction is extended to the SU2L cross SU2R. Well, that is not really a unified theory, but some big important step into the unified theory. The first unified theory is the Georgia-Glashow model. It's built in the gauge symmetry of SU5. Matters are arranged in 5 bar and 10 which are some irreducible representation of SU5. And then some other like the mediators and Higgses here I will not repeat. Well, unfortunately, the neutrino, right-hand neutrinos are not included here. So neutrinos are massless, and that's at that time. Then all these groups can be included into a bigger framework, the SO10 guard. This shows how the SU5 can be embedded into SO10, and this is how the Paddy-Salam model can be embedded into the SO10. But more than that, some other groups can be included into the SO10 framework, like the SU5 cross the additional gauged U1B matrix L symmetry, or the flipped SU5. Considering with the former SU5, it flip the U-type quark with down-type quark and the neutrinos with charged leptons. Well, okay, so you see, these models have been proposed just exactly half century ago. It's a long time, but so why we still study this old theory today? Well, I give my reason in a phenomenological point of view. First reason is the upcoming large-scale neutrino experiments. Juno, Hyper-K, and Duo, they will take data, or they will actually Juno has been finished for this for the setup, and it will under operation very soon. And Hyper-K and Duo will complete their constructions in the coming few years. They will measure proton decay into a better sensitivity. In particular, the Hyper-K will give the constraint to the proton decay by 1 order of magnitude higher. But more than that, they are precision measurement of neutrino physics. Well, and they in some sense, since now neutrino, we know the quarks and leptons have been measured precisely. Now neutrino sector will also be measured very precisely. This will be considered as another important constraint to the guard. Reason 2, the undergoing and upcoming gravitational wave measurements. We have the ground-based, space-based laser interferometers, and also the PTA, the pulsar timing arrows measurements. So I will show you how they can give us some hint to the guard. Okay, this is the phenomenology of a summary of the phenomenology. God can provide a lot of different things. Well, it's hard for me to really introduce every sector here. Here, I mainly focus on these 3 parts. First, proton decay, as I just said, this is some classical and standard proof to the God. Second, Fermi mass mixing, and the third, gravitational waves. Well, not all of these God can predict the gravitational waves, but most of them, if they can produce them, if the inflation happens in the correct place. Yeah, first one, proton decay. Since the God unified the quarks and leptons into the same representation, or in a series of representations, then there could be some mediators can transfer the baryon to lepton. The first one, the dominant one, is the mediator is the gauge mediators. At the low scale, much lower than the God scale, but above the standard model, the electric scale, it appears as the dimension 6 operators. With the harmonization in the in their initial state and the final state, we get the proton decay, and the main channel is proton to pi0 E plus. For the gut scale about 10 to 16 GeV, the typical lifetime for the proton and like for this channel is 10 to 35 years. Well, if there's a if we are working in a SUSY version, there could be additional dimension 5 operators like this one. It's the operator with 2 fermions and 2 s fermions. After it's stressed, it can also mediate the proton decay, and one of the main channel is the proton to K plus mu bar. It can be enhanced by the SUSY mediator. Okay, I'll show you how simply explain how a neutrino measurement can measure the proton decay to a very high sensitivity. Consider these kinds of water tank or the liquid scintillator. This is the typical size of Juno and Super K, 20 ton. It's very easy to estimate that there would be around 7 by 10 to 33 proton. And I think we have so many protons there, and let us store in the here for 1 year. And we have a lot of like PMT or some other detectors around it. And let's say if any of the proton can decay and generate some signals to be detected by these detectors. Well, if none of these protons are decayed, there will be no signal can be detected. Then that means, let's say 1 year, okay? 1 year for one proton, now 7 by 10 to 33 year, 7 by 10 to 33 proton for 1 year. That if no signal is generated, that means the lifetime for the proton should be larger than 7 by 10 to 33 years. And of course, that is just some very ideal and simplified analysis. In the reality, in the experiment, we need to consider the efficiency of the detector and some statistic factors. But this part for us as theorists just to provide some order one corrections. It may suppress the sensitivity a little bit, but the correction will not be too large. So this one shows how the Juno can, after a few years, how it can give us the constraint to the proton lifetime. And we have later have the better hyper K and then Dune, how they, in summary, how they can constrain the proton lifetime and further constrain different types of grand unified series. Yeah. So for the first channel, typically hyper K will give the constraint to 10 to 35 years compared with the current constraint around 10 to 34 years. And in the future, another channel, K plus mu bar, the future constraint is around 10 to 34 years, and eventually will enhanced or close to 10 to 35 years. And you'll see how different kind of gut models can be excluded or proved. Okay. Any questions? If no questions, I will continue. Then so well, okay, back to the SO10 gut and see how the SO10 gut models can be constrained in this experiment. Here I show a few examples of the breaking chain, like here with 2 intermediate scales, SO10 to G2 to G1 to the standard model gauge group. Here G2, G2 and 1 are shown here. Yeah, different, like here, the Patisala model, and then the left-right symmetric model, and then finally to the stand model. I show how for different breaking chain, the lifetime can be constrained. You will see all of them satisfy some very clear power law between the lifetime with the Gas scale, and the constraint to the Gas scale is similar in all these chains. Here currently about 3 by 3 to 4 by 10 to 35 GeV, and in the future close to 10 to 16 GeV. Okay, then second part, the Fermi masses and mixing. So why this is important? The main point is that the precise the area of precise measurement of neutrinos is coming. Currently, the best measured parameters in the neutrino experiment is around, the sensitivity is around 10 to 10 to minus 2, 1% level. In the future, in general, it can reach 0.1% level. So the neutrino sector will be measured more and more precisely in the future. Then what? Why it matter? Here I show you. In SO10, we have all the quarks leptons arranged in a single 16 dimensional irreducible representation of SO10. Then you see the most generically we can construct the Yukawa interactions here and get how the different Fermion Yukawa couplings can be generated from the general Yukawa interactions. Here is the result. So down type quark and charged lepton, up type quark, neutrino, Dirac Yukawa coupling, they are all correlated by linearly correlated by dependent on 3 by 3 Yukawa couplings. Here I just simplify simply writing them as H, F, and H prime. And the right-hand neutrino is just determined by F up to overall factor. So, well, we know this here, and here, and finally after the seesaw mechanism, the neutrino masses can be measured. We have 4 mass matrices measurement on the left hand side, but we have 3 free matrices on the left hand side. That means these masses are correlated. Well, by considering all the known up-to-date data in quark sector, charged lepton sector, and neutrino sector, here we can fit all the data and also get the constraint to the free parameters of the of SO10 models. Here just to show some finally the output of some correlations. Here is the correlation between theta 2,3 in the lepton sector with the leptonic CP violation phase. We can further not just that, since here is the right-hand neutrino masses, we can further predict the mass spectrums of right-hand neutrino masses. Typically, the masses, the lattice masses, it's between 10 to 11 to 10 to 12 GeV. The heaviest one is around 10 to 13 GeV. And another case is in general we predict normal mass ordering for the lattice neutrinos. That means the little m1 smaller than little m2, smaller than little m3 here. But we cannot make the conclusion that the inverted ordering cannot be predicted, because that really requires a very large scale simulation. But we cannot do that. So Anyway, the normal mass ordering is preferred. Well, we can in principle we can generate all the, you see, we have all the conditions, and we can also predict all the Yukawa couplings. In the neutrino sector, we already have the masses, and we can also predict the Dirac-Yukawa coupling here. After some basis of rotation, we can use that to check if the matter-antimatter asymmetry can be generated by leptogenesis with the correct amount measured by in cosmology, and we'll see some of these points can generate correct amount of matter-antimatter asymmetry. Here they are shown in blue. Well, we use the code of Unisys to do the job. Then the third part, the gravitational waves. Well, the how here. Well, grand unified theory, in most cases, we just consider it's the particle constraint. Then how it can be connected with its cosmological measurement. Here, just a very brief introduction of the mechanism. First is that most of the gas, exclude the simplest SU5 case, most of these gas include U1b minus L gauge symmetries as a subgroup there. And the spontaneous breaking of this U1 symmetry generate cosmic string, which is a topological defect as granted by a mathematical theory. Well, and these strings they can oscillate, they generate gravitational waves. Well, I'm not going to discuss more details of this cosmic string, the mechanism of cosmic string, to generate the generation of gravitational wave from the cosmic string, but just to show a simple example that you see we oscillate when we play a guitar, the string is oscillating and we get a sound wave from it. So similarly, if the cosmic string is oscillating, then it can generate the gravitational wave. Phenomenologically, this is the result. We can have the stochastic gravitational wave background to be measured in these different kinds of gravitational wave measurement observatories. And the frequency spectrum is shown can appear in a very wide band from 10 to here, the nanohertz, to here, kilohertz. Well, I don't care too much about it here because this part we have now, currently we don't have any experiment can do that. Yeah, first feature is that it has a very wide band. Second, at the high frequency, the intensity, or more precisely, omega h square, is proportional to the square root of the tension, and then it's linearly proportional to the B mass L breaking scale. So this is a very brief and very simple clear feature to connect the signal of a gravitational wave with the B mass L breaking scale. Well, okay, then this is just the B mass L scale, but how it's connected with the gas scale? I can further show you one example. We consider this breaking chain. SO10 breaking to the Paris-Salam with the left-right parity symmetry with the left-right symmetric gauge symmetry and finally to the standard model gauge symmetry. Here we have two intermediate scales and labeled as M1, M2, and then the gas scale shown here. If we assume the M1 is around 10 to 11 GeV, to unify all these three gauge couplings, we can constrain these unified three-gauge couplings means we have two equations. And these two equations can determine, once M1 is assumed, these equations can determine M2 and M gut. If we change the value for M1, these two equations will determine M2 and M gut at different values. So this is the idea. Basically, M1 here referring to the Beam-mass L breaking scale, but in most cases, because this is an Abelian scale, Abelian symmetry, that is really broken finally. So M1 and M gut are always correlated. But if for different chains, the correlation could be different. So here, if you remember before, here it shows the correlation between the proton decay lifetime with the gut scale. And now, if we consider about the correlation of the gut scale with the Beam-mass L breaking, then we get the correlation between the proton decay lifetime with the intermediate scale M B-1. Well, it depends on the different chains shown here, as I said. And here, this part has already been broken, has been ruled out. And here, this part will be ruled out or proved in the future, and this part cannot be proved in the future. Well, this analysis is based on some economical hypothesis that if we consider only particles which are necessary to generate the masses in the standard model particle masses or to break SO10 to the necessary intermediate scales. Okay, if we consider this is the constraint and finally this is something left for the scale for B-mass L, and we can change this information to the prediction of the spectrum of gravitational waves. This shows these different chains. There are some other chains that I haven't shown in here, but they are considered in our paper in a systematic way. All chains of SO10 all different break chains of SO10 has been considered, basically. Yeah, about the final part of my talk is about the influence of the recent PTA measurement. So in the last summer, we have all these collaborations report about the potential hint of the gravitational wave signal. Well, so let's say, well, we don't know if it's from the cosmic stream, but as seriously, let's say if this potential gravitational wave signal is from the cosmic stream, how far we can go there? Okay, and this is show some signal shown in the nanographs paper. It's around in the nanohertz, here nanohertz, 10 nanohertz, and here 100 nanohertz. It shows some kinds of signal, you see, with a relatively large gradient and a relatively high intensity. This is the signal. Then compare with the signal, the prediction of a cosmic string gravitational wave. Can we explain that? In the simple case, if we consider just the Lambda string, well, the spectrum depends on only one parameter, the tension of the string, or let's say the scale B-mass, the B-mass L scale. If we enhance the B-mass L scale, then we can get larger omega h square, but here the gradient is almost zero. If we want to get a sharper spectrum, we have to suppress the B-mass L scale, but the omega the intensity or the omega h square will be much smaller. That's the problem. In this simple case, we cannot explain the gravitational wave signal from PTL or from the land graph. So then what's the solution? There could be several different solutions, like the superstring, or here in the grand unified theory, that's the metastable string. This is another solution. How I'll give the explanation of why this metastable string can explain this gravitational wave signal. So if the strings is not stable, but if it can decay to stable means they will not decay to the other channel except the gravitational radiation. Here I said it's not stable because that means it have some other decay channel. The decay channel shown here is the monopole anti-monopole pairs. If they can decay to some to the monopole anti-monopole monopole pairs, that means the string will have a lifetime, a shorter lifetime. So in this spectrum, this part in the high frequency band, that is referring to the gravitational radiation from the string in earlier time, and here in the low frequency band, that means the radiation gravitational radiation at a later time. If the cosmic string has a shorter lifetime, that means here this part the spectrum can be separated into a sharper grad with a sharper power law. Then if we want to insist this sharper power law, we can, to enhance the intensity, we can increase the B minus L breaking scale to make it higher to here. To enhance it to the higher to around this range, we need the B minus L breaking scale very close to the gut scale. But yeah, the B minus L breaking scale should be very close to the gut scale. And on the other hand, the B minus L breaking and generate cosmic string, and it's well known that the gut breaking can generate monopole. So that means the masses for string, the scale for the string and the mass for the monopole are close to each other. In that case, the channel for the monopole anti-monopole pairs can be open once their scales are close to each other. Okay, that's the idea. Then how these kinds of, so here is the conclusion. We have the B max L breaking scale should be close to the M guard. And this M guard should be, satisfy all the constraints in the neutrino experiment and protein decay measurement. How this can be satisfied? We cannot have this one too low. It should be still around 10 to 16 GeV, not far away from there. But that means we have to enhance B max L. But if we see some the Lang-Soucy case here, the scale of this B max L scale, let's see here, it's hard to enhance to. It's hard to make this scale to be to a very high. So we consider some variation of the gut. One case is the Soucy case. We extended the Lang-Soucy SO10 to the Soucy SO10, so it's very natural to enhance the B max L scale to around 10 to 15 GeV. In this case, we can produce we can generate the spectrum. Some other effect should be considered here. But anyway, it works. Well, On the other hand, in the particle physics, we should consider some constraint. In the SUSY case, the proton decay into a K plus nu bar channel is open. Then we should consider the constraint of this channel. Here, this part has been excluded. And here, this part will be tested, can be tested in the future. Here, this part will never be tested in the future. Another case is flipped SU5. Flipped SU5 provides some different feature. The U1 scale for the cosmic strain is almost independent of the gut scale. So you can actually assume it at any scale. So of course, then you can assume the U1 beam matrix L scale very close to the gut scale. So then that's the case. Well, and this kinds of unified theory has another feature totally different from the former part. That is the lifetime for a proton decay is very, very long. It's almost impossible to be measured in the future hyper-K measurement also, or the other neutrino experiment. This is just for the pi 0 E plus channel. For the K plus nu bar channel, it's forbidden by some missing messenger mechanism. Well, sure, and we can further check. We can also check if the reproduction can happen in these different kinds of gas models. In the SUSY SO10 case, and there's no doubt it can produce, and we have done that. I'll not repeat here. But something funny is in the flipped SU5, if we can achieve the reproduction, well, like even we may think it cannot. The reason is not shown here. In the flipped SU5, the up quark and the Dirac neutrino mass matrix are identical to each other. If we consider the seesaw formula, here we have this part is around 0.1 EV, and here we'll get a very hierarchical. It's natural to get a very hierarchical right-hand neutrino masses. So here, like just shown here, the heaviest one probably around 10 to 14 GeV, and the next one you'll see how low it is. Just
we have 5 minutes left.
Okay, I'll finish soon. So this one is just not far from the unit weak scale. Such no scale, it's not very hierarchical. These kinds of spectrum cannot be used to generate the Neptune genesis. Well, but this is just some naive estimation, but that's actually not true. In some of the parameter space, with some special flavored texture assumed, we can have the nearly degenerate masses for the lighter two right-hand neutrinos. And you'll see here that their masses can be just around 10 to 9 to 10 to 10 GeV. In this case, thermal reproductions can work, and we're happy that to generate the enough matter-antimatter asymmetry. Okay, then that's the summary. Well, I just shows here just the figures show how the different kinds of phenomenology can be connected to different parts of the gut. Like the proton decay give us the constraint to the gut scale. The gravitational wave measures hinted at the beam matrix L scale, and these two scales are connected by the grand unification. Well, and further, something should be considered is that the correlation of a quark masses and the lepton masses and mixings there, and we also can extend the discussion of gut to the leptogenesis. Yeah, that's all my talk. Thank you.